All right, welcome everybody to this week's Geoscience Australia public talk, and this week we have a fantastic presentation. It's one part of our Geoscience Australia Distinguished Lecture Series. But before we move on to that, I'd just like to introduce myself. I'm Andrew Heap, substantially the Chief of Minerals, Energy and Groundwater Division, which is where this work is happening. And so I'm very proud to to introduce the public talk today. Before we get started, I'd just like to acknowledge that Geoscience Australia values the lands, water and sky as we work to deepen our shared understanding of country and earth, and we pay respect to First Nations peoples and their enduring connection, contribution and obligations to country, reflecting on their shared history, and we are committed to listen and learn. So today we have a fantastic presentation from Babak, who's going to regale us about how we listen to the Earth's whisper, which is fascinating and very intriguing. Looking forward to it. Today, the focus of his presentation will be about how the key work that they're doing in the team, he's presenting on behalf of the team, how the key work of the team is really to understand the geological prospectivity of the country, but using some very, very sophisticated and complex technology to do that. So you'll see some of that today. A little bit about Babak. He's a seismologist with a PhD in seismic imaging and with more than a decade of experience studying earthquakes and earth structure. He first came to Australia in 2015 as a research fellow at the Australian National University, focusing on seismic source modelling and lithospheric structure across the Australasian region. His research has advanced understanding of how seismic waves can be used to image Earth's crust and mantle with increasing precision. He now leads Geoscience Australia's efforts in ambient noise tomography, developing new approaches to map Australia's subsurface and reveal the continent's hidden geology. Please welcome Babak to the stage.
Okay. Hello, everyone. Thanks for coming to today's talk. I'm Babak Israni, as Andrew mentioned, on behalf of the passive seismic imaging team here at GA and many other teams that helped bringing this program to this stage. So today's talk is about listening to the Earth's whisper, and I'll explain what I mean by that and how we use that to image the Australian lithospheric structure. So, go to the next slide. No? There you go. So we acknowledge the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognize their continuing connection to their land, water, and culture, and pay our respect to their elders, past and present. So right now, beneath our feet, the Earth is vibrating. We can't feel those vibrations, but we have developed instruments sensitive enough that can detect and record them. Why does the Earth constantly vibrating? Well, to name few sources, interaction of ocean wave with solid Earth, anthropogenic noise, that's us, we make a lot of noise, and then earthquakes, just to name a few. That's an example of a record of background ambient noise on a station WRKA from the Australian National Seismograph Network. And that's when an earthquake happens in Papua New Guinea, okay? So the signal gets interrupted by earthquakes. When we look at the signal, the background noise in frequency domain, the time, the x-axis is still time, the y-axis is frequency, we can see that the background noise is a faint, we call it background noise, but it's a faint signal at 0.1 hertz to 0.2 hertz mainly. But when an earthquake happens, it all gets interrupted by an earthquake, which covers all frequencies, from very low frequencies to high frequencies. So I want to go over some of the contributions of global seismology to our understanding of the Earth's dynamic and its Earth structure. I think the early contributions from global seismology was to plate tectonics. This is an image of global seismicity, which was taken in the year 1857, almost 170 years ago. But it was the early images in the 1930s that really solidified the plate tectonics, because scientists realized that the earthquakes are happening where the plates are rubbing against each other. So that was one of the concrete evidence for plate tectonics. I believe the next big contribution from global seismology comes from Inge Lehmann, a Danish seismologist, that proposed that the Earth has a solid inner core within a liquid outer core. And she did that by analyzing P-wave arrivals, and the argument there was that if you don't have a liquid, if you don't have a solid inner core, you don't get these waves that are bouncing back towards the surface. The next big contribution from seismology came along with seismic tomography was born, and it happened after the global seismograph network was developed, covering most of the surface continental areas around the world. And it also happened around the same time where there was a groundbreaking advancement in seismic imaging. The first person that created a CT scan machine, Godfrey Hounsfield, was a British an engineer that created the first image of a brain on the 1st of October 1971. And the idea was very simple. If you shoot X-rays from one side of an object and record it on the other side, and you keep doing that around in every angle, you can push all those information into a computerized tomography, what they call it here. CT scan stands for computerized tomography, and they call it some serious number crunching. We call it geophysical inversion. Then you get an image of how the density within that object is changing. So it's not an image of the object itself, it's a variation of a property within that object, in this case density. I took a CT scan about 3 years ago, and then after that I saw this video online. So this is a view of how a CT scan machine works. This machine rotates at 150 rounds per minute. So I'm really glad that they covered it up, because if it was working like this, I wouldn't go into it. But it is necessary, okay? It is necessary if you want to get, a full image of a medium, you need to shoot from every angle and receive it on the other side. So you need that full coverage, which is what this machine does. And with the advancement of it, it is remarkable that we went from an image like this in the 1971 to a high resolution image that you can take today. So that gives you the density variation, because there is a difference between the density in your bones compared to your muscles, for example. Now, Keith Archie was the first person that realized that we can utilize this for the Earth. Obviously, we don't have a giant CT scan machine. That's an AI-generated image. But we have earthquakes, right? So that's our source of energy. So seismic rays travel from earthquakes through the Earth, and then they get recorded at seismic stations. So that was the first idea that gave birth to seismic tomography. But the interaction of seismic waves from an earthquake with the Earth is far more complex than an X-ray shooting from one side of the medium, any medium, to the other side of it. Here we have P-wave, that are first waves that arrive, and they are directional, and their propagation is in line with the particle motion. Then we have the secondary wave, or shear waves, where the direction of the propagation is perpendicular to the particle motion. And then we have surface waves, that they only travel near the surface, and their particle motion is elliptical. So we get a range of seismic waves that travel through the Earth. So Archie had to pick and choose. So he picked the simplest one, the P wave. But even this simple one, you can see that, you can see that the interaction of a simple P wave through the Earth, this is an image simulation by Michael Thorne from University of Utah. It's still complex, but you can have that arrival, that first arrival, the time of that first arrival explained by a simple ray from the source to the receiver, from the earthquake to the seismic station. And that's what Archie used to do a seismic tomography of the crust and mantle beneath Norway. Now, there are big differences between seismic tomography and medical tomography. In medical tomography, you have full control over the sources and receivers, so it's an over-determined problem. It can be solved without regularization because it fully covers the medium. There are very minimal smearing and artifacts in medical imaging. There's no to little error in the location of the source and receiver because it's controlled by us. And it's also very little error in the measured data. Those are all different in seismic tomography. In seismic tomography, we don't have any control the way that Aki did it. We don't have any control over the sources. Those are earthquakes that we don't have any control over them. So it will be a mixed determined problem. Some areas are hit by rays, some areas in your model, as you can see in these empty cells, are not hit by any rays. Also, there will be errors in the location of those earthquakes that we estimated, and there will be errors in the data that we have picked. So, and for that reason, the seismic tomography is called the art of seismic tomography. Okay, it really depends on the subjective choices that the expert is making to deliver a reliable Earth image. Okay, which we will touch upon today in some of the examples. Okay, so those were the contributions of global seismology up until 2000. But in 2000, a new idea came along. And it was that is this part of the waveform, the one that we historically called noise and completely discard, does it contain any information? Is the only information that we get is from P wave, S wave, and surface wave, or this also contains some information? When you look at this as a close-up, there's not much to see there. It's just, it looks like random wiggles with no clear pattern that you can recognize. However, if we look at in terms of observations, we know that ambient noise in a background contains information about our daily life at high frequencies. Here's an example from a study in 2021. So you can see over the Christmas, New Year, the Earth in general at high frequencies is quiet. Okay, so we're not around. We're just at home celebrating Christmas, I guess. And then when the COVID hit, which was lockdown on days, so on y-axis you see the name of cities and the seismic stations that they will deploy them. I think Canberra is down here. So you see after COVID lockdown, everything goes quiet. Okay, that's one example of background noise observation. Another one that I personally like is whales, blue whales. We can listen to blue whales and how they call each other and how they talk to each other. So this is a recent deployment, an OBS deployment in the western coast of the US. And you can see there's a repetitive signal. There's a repetitive pattern in the background ambient noise. And when you zoom in, this has been interpreted as whales calling each other. So this is calling each other with different names. So there's A call and then there's B call. And we can even track them based on how they call each other and where they're going. Okay, by triangulating between what's the distance between each call from each station. And this is a track. So this is a track done by seismology. Those whales, there are no GPS attached to them. This is just us detecting them talking to each other and tracking where they go. And even more than that, we can track how fast they go. This is a velocity profile and how blue whales travel. So in terms of observation, there's abundance of data in the ambient noise. But the question is whether we can use ambient noise to image the Earth structure. Can we turn these wiggles into a tool to image the Earth structure? And that came along with interferometry. So interferometry uses the cross-correlation of two signals and measures their similarity. An example here, two sinusoidal oscillations. They move through each other. That's what we call a cross-correlation function. When they perfectly match, the function is 1. When they don't match, the function is 0. And when they are exactly opposite of each other, the function is -1. A very simple operation. But it has huge implications. The recent images of the black hole in two galaxies, Sagittarius A star and M87, were done using interferometry. But in terms of seismic tomography, you can use a very simple interferometry or cross-correlation between two stations and measure how long does it take for the signal to go from one station to the other. An example here is shown. You have two stations, station A, station B, and the signal goes from left through those. So it arrives at station A at time A and at station B at time B. And the cross-correlation function would just measure the time difference between these two. So it's telling you that the signal will go from here to here with a time delay of TB minus TA. Very simple. Now, if the signal is is noisy and contains multiple sources of energy, it still works. The cross-correlation function still tells you, even in such a complex signal, that it takes about 0.06 seconds to go from station A to station B in this case. Now, if the signal is two-sided, so two sources of energy from left and right, you still get that measured as a causal and acausal part of the cross-correlation function. So you can measure one signal going from one station to the other by just simply cross-correlating their signals. Okay, so, but the theory of ambient noise is telling us that the distribution of sources of energy around us is not just left and right, it's everywhere, 360 degrees around us. Take Australia, for example, surrounded by the oceans, and oceans are interacting constantly with the solid earth. So that sources of noise is everywhere around us. But the theory of ambient noise in this case says, well, when you take an average, the ones that are at minus 90 degrees and plus 90 degrees, they cancel each other out. Okay? Their interaction is destructive. But the ones that are at 0 and 180 degrees, they are constructive, so they amplify each other. I'm a very visual person. I like to visual things. So here's an example of two stations, EIDS, MEK, and K in east and west of Australia. This is a perfect example. Australia is a natural laboratory to test these things because we're surrounded by the oceans, by sources of energy. And a 1 hour cross-correlation of data between these two stations will look something like this. Not much to see. If I repeat this 60,000 times, there's still not much to see. Okay, individual cross correlations, there's no information in them. But when we start to take an average, and I'll do an animation here where progressively I add hours, you start to see how the signal starts to form. After 1,000 hours of cross correlations, you can see a signal starts to form. After 9,000 hours, which is about 1 year of data, you can see a stable signal. And in this case, I had 60,000 cross correlations, so I just added them all up because these two are permanent stations recording for 20 years now. So clearly, we can construct a signal, even unto stations that are far side, the two end of the country, 3,000 kilometers apart. And remember that this signal was recovered from a faint ambient background noise of oceans interacting with the solid earth. Okay, so we're getting a signal, and that's a window that I expect to see a signal. We call this noise correlation function. So there is a surface wave-like. It's not exactly surface wave, but it has the properties of surface wave. And it is, which we call signal, and then there is a precursory noise. So if you want to calculate the signal-to-noise ratio and measure how good your signal is, you can in this framework. So noise correlation function, that's what gave birth to ambient noise tomography, which is going to explain now. Okay, so let's break down this signal. We filter it at various frequencies. Low frequencies are shown at the bottom, and progressively higher frequencies toward the top. These low frequencies are sensitive to deeper part of the Earth. So the deeper part of the Earth's velocities are faster, so these travel faster, so they arrive early. And the higher frequencies, they're sensitive to the shallower parts of the Earth, lower velocities, so they arrive late. So you get this arrival that is progressively later and later. And that's what we call a dispersion curve. This is our data, okay? It tells you at each frequency, seismic waves are traveling with this velocity. Okay, so the real bottleneck in this workflow is to calculate these dispersion curves between each station pair. And now that's, historically, that has been a manual, tedious job because you have to sit down and pick those arrival times. But an old idea by Aki, 1957, he pointed out that you don't have to do that in time domain. You can actually do it in frequency domain and match your spectrum with Bessel function. Okay, Ekstrom came along in 2009 and said, you don't have to match the full spectrum, only the zero crossings. I'm not sure you can see the red dots here, which is the zero crossings of these functions. So from those two, you can get candidates for what your dispersion curve would look like. Obviously, among these 5 candidates, these 2 at the top and these 2 at the bottom are not a good candidate because they go to plus infinity and minus infinity at low frequencies. The only one that represents Earth-like structure, Earth-like velocities is this one. So this method lends itself to automation quite easily, okay? Despite the other one, which you had to pick manually in time domain. But there is a problem. Okay, before the problem, yes. Goran Ekström applied this to the continental US using AusArray data. Great results, but there is a problem here. And that is it always this good? Are these dispersion curves in this automated workflow always look this smooth and reliable? I can report that only 10% of my data actually look like that. Also, can you push towards higher frequencies? I would like to go to frequencies beyond 0.5 hertz, because that's where the surface wave becomes sensitive to the shallow structure, okay? We want to image the Earth structure all the way from the bottom, from the lithosphere, all the way to the top, because ultimately, from mineral perspective, if you want to know the depth of the cover, the depth of the sedimentary cover, those high frequencies are extremely important. But you realize that the Goran Ekström, actually, the Ekström et al., they stop at 0.1 hertz. They don't go towards any higher frequencies. Okay, so those are the two main goals. I'll show you 3 examples, and I'll show you how an algorithm that I have developed is taking care of these problems. So a good example, like the one that Goran Ekström et al. Are showing in their study, I call it good, would look like this in my data set. I have other examples, which are majority of my data, that include sudden jumps and what I call a smooth jump, okay? In which the velocities do not represent anything that we know about the Earth. The velocities in Earth don't jump from one point to another by half a kilometer per second. That's just not, Earth is a continuous medium, okay? The velocities don't jump. So clearly, if I am picking these manually, I won't go up, I will go from here to here, and in this case, I'll go from here to here, so I'll connect them manually. But I want a workflow that does that for me automatically. I have 15,000 cross correlations the first phase of our deployment, and there's going to be hundreds of thousands cross correlations. I don't want to spend time picking these manually. On top of that, I want a metric of quality, because these 3 examples at the bottom, these are good data and these are salvageable data, but they are data that are just total chaos. There's no pattern in them. You can see that the dispersion curves it doesn't look like anything we know about the Earth. So I want a metric quality that tells me that that's bad, that's good, and these are salvageable, and that's a way to salvage them and get an Earth structure. Now, anytime that there's a problem like this, these days, AI come into the equation, convolutional neural network. You want to develop a neural network that you have some labeled data, good data, bad data, and you train it on that data, and you expect it to work everywhere. So I'm going to take a break from seismology, and I'm going to show you a few fun examples. This is from a YouTube video by Alex O'Connor. You should check it out. It's amazing. So show me a full glass of wine. You're asking a large language model. It's not full. It's half full, okay? And I say, no, I said a full glass of red wine. It's still half full. And then you say, does that look like it's filled to the brim to you? So now, yes, it is filled to the brim, so it gives you another image. And then, wait, it's still only half full. Now it's trying really hard, and I really like this example. It's pushing it up as much as it can to touch the brim, but it's obviously not. So it doesn't have an understanding of what it means for a glass of wine to be filled all the way to the brim. It can show you an image of a glass of wine with wings, okay? And the reason for this is that because it has seen a lot of glasses of wine filled up to a drinkable level, what humans just drink, and it's also seen a lot of wings, so it can put those together. So it's really good at complex ideas that are an interpolation between multiple ideas, okay? But if you want to extrapolate, if you want to go beyond what it's been trained on, there's no success usually. Now, there's another one that is my favorite. Now, this is my second favorite. My actual favorite comes next. But it says, show me a glass of wine with only a tiny drop of wine in it. The half full is still there, but then the tiny drop shows up. Okay, now this is my absolute favorite. So it's telling here is a wine glass filled to the absolute limit. a liquid slightly overflowing and trickling down. No, it's not. It's not full. It's still going through the glass, okay? Now, this was version 4 of that large language model. 2 months ago, version 5 came out, and yesterday I tried to replicate this to see whether the version 5 is better, and I have to report that it's actually better. So version 5, after 3 iterations, it can show me an image of it. So it's just telling you that how fast these large language models are progressing. It's moving forward, breaking the boundaries that they didn't used to. Okay, let's get back to seismology. So that was the reason I didn't go down the path of generating a large language model, not language, a convolutional neural network or any type of AI machine, because I don't have a large labeled data. And even if I have a labeled data set, it doesn't guarantee that it will be able to successfully pick dispersion curve that it hasn't seen before. Okay, but there are still solutions, and I'm going to show you what I've done here. You notice that this part, this is the noise correlation function in frequency domain. We call it the real part of the spectrum. You notice that this d distance, as the distance increases, the spacing between the zero crossing becomes smaller and smaller. And I can show you a few other examples. So when the station distance is 3,000 kilometers, those zero crossings are really, really close to each other. They're almost on top of each other, okay? Now, I thought that there might be a relation between these two, okay? So I calculated 27,000 noise correlation functions for all stations within the Australasian region. And I plotted, I have to read this. It's average of spacing of zero crossings of the real part of the spectrum of noise correlation function, which is quite a mouthful. Let's just call it S, hertz. And then the interstation distance. Let's just call that D, okay? There's clearly a relation between these two. Sorry, the relation, I swear it's there, yeah. So there's a relation between these two, and we can fit a curve to this, a curve of form 1 over x. And I call this zero crossing distance scaling, ZDS for short. So why is this useful? Well, given any station pair and the distance between them, this gives me what I can expect as an average spacing between these zero crossings, okay? So hold on to that thought for a moment, and then let's go back to the examples, the good, the sudden jump, and the smooth jump. For the good jump, most of these zero crossings are very are evenly spaced, and they are very close to the value that is suggested by the ZDS. You can see them here, okay? That's S from this formula, and these are the zero crossings and their distance from S, okay? You can see that the actual signal, the precursory noise is actually quite strong. So if you calculate the signal-to-noise ratio, the signal-to-noise ratio is pretty low. It's 1.9, so you will most likely be discarding this data if you go by signal-to-noise ratio. But if you look at the spectrum, it's perfectly evenly spaced. The dispersion curves look quite smooth and reliable. And this is what happens when the zero spacings are very closely are within a close proximity of that ZDS value. Now, in the case of a sudden jump, that's where you have missed a zero. That's where you have missed a zero crossing. So this is the sudden jump. If you were picking this by approach by Garn-Ekstrom, that's what you were picking. But what I do here is when I encounter a missed zero crossing, I just jump to the next branch. Next case, which is a smooth jump, this is a bit more complicated because you don't have a missed zero crossing. They're just not well placed, okay? They are misplaced slightly, and that causes those variations in the dispersion curve. In this case, I calculate average dispersion curve behind this point, called GC, and I calculate gradient, average gradient behind this point, called GC, and the gradient from this point to every other point on those candidates. And then I minimize the difference between these two. And the location that gives me the minimum difference between the two smooths the dispersion curve, okay? So these three examples that I showed early on, I didn't pick them manually. They were all picked automatically by this workflow. So just 3 classifications of zero crossings with relation to ZDS solves the problem of having irregularities in the dispersion curves. Now, remember that I wanted a metric of quality as well. Well, that could be easily achieved in this workflow. You could take get all the zero crossings that are in class A, these are very closely tied to ZDS, and divide it by the total number of zero crossings. If they're all well placed, that would be a perfect score of well-placed zero ratio, or WZR of 1. Okay, so in this case, in the perfect case, in a smooth dispersion curve, the WZR would be 1, and if you have missed zeros or badly placed zeros, that WZR decreases. Let me show you how does that give me a metric of quality for dispersion curves. Well, I've plotted the WZR, that's the y-axis, against distance, and I want you to look at this bit in the inset up there. For a lot of dispersion curves, okay, with WZR of perfect score 1, these are perfect data and you should be using them, we have very low signal-to-noise ratio. Traditional seismologists will discard all of these. I mean, I'm a traditional seismologist, but traditionally we were discarding all of these data, right? But now, according to WZR, we should be including. These are very good data. And why the SNR is behaving like that is because this deployment was right next to the Gulf of Carpentaria in Northern Territory. And the Gulf of Carpentaria is a major source of energy, okay, the ocean waves interacting with the continental margin. So if a station is facing towards the Gulf of Carpentaria, there will be a high signal-to-noise ratio. It's all shown here. And if a station is placed perpendicular to the Gulf of Carpentaria, it will have a low signal-to-noise ratio. So if you go by signal-to-noise ratio, I really like this plot, this circular plot, because it's a nice analogy to the CT scan problem, in which if I go by signal-to-noise ratio and pick only dispersion curves that are in this direction, it will be similar to a CT scan machine that doesn't rotate. It just takes all the images in one angle, and that's not a good image. Okay, so let's put all of these to practice. First application that I'll be showing is from AusArray. AusArray was part of the Exploration for the Future program. I will show you an example of the first deployment of AusArray, deployed in 2016 to 2020, half a degree covering the Northern Territory in this box that you can see. If I go by the idea of Archi, these will be my dispersion curves. Okay, they're all over the place, huge variations in them. And if I generate a tomography slice at 0.2 hertz or 5 seconds, it will look like this. Okay, hold on to that. Now, if I go with my dispersion curves, using my algorithm and the data of WZR larger than 0.8, the dispersion curves will look like this. Okay, no manual intervention. This is fully automated. And the Earth structure will look like that. Now, the other benefit that I wanted to go all the way towards higher frequencies. So if we can go to 0.4 hertz in this case, and this is the highest frequency slice that I have generated here at 2.5 seconds. So you can think of this as a slice through top 2 kilometers of the crust. Very interesting features now. Amadeus Basin is showing up as a low velocity. I forgot to say that red is low velocity, blue is high. Mount Isa, high velocity. Carrara Basin, was newly discovered basin, is also low velocity. And even the Nalia Basin, this is a tiny little basin that is over there, and I was really surprised to see that we can even recover that, okay? So all the basins are showing up. The Carrara Basin is not in this image because this image was generated in 2019 where the Carrara Basin wasn't discovered yet, but this image is already showing us all of that. So I think this really validates the workflow. If you don't include this workflow and the WZR and the things that I've explained, you will end up with this image. Good luck with interpreting that. But if you go with that, this is the image that you will be interpreting. Much easier to interpret, much easier to correlate with geology and what we know from the near surface. Okay, so let's see an example or application of it to the entire continent. On the second phase of EFTF, 2020 to 24, we deployed a 2-degree deployment across the country. I would like to take a moment to acknowledge all the people that have contributed to this. We will continue this work through the Resourcing Australia's Prosperity Initiative, and we will be covering the entire country with a half-a-degree deployment by the end of RAPI. But this was a very difficult task. Remote and challenging environment. A lot of these stations were deployed in places where there were no road access, so we had to use helicopters. The temperatures during the day go up to 45 degrees in shade. And anything that could go wrong went wrong. COVID hit, so we couldn't travel between states. Then came the floods, then came the fires. We deployed stations that we couldn't service them for months. So lots and lots of challenges. But I think we have successfully overcome them. The deployment of these stations, you can see a sketch of how the stations are deployed. They deployed 0.5 meter down the earth, and they covered with a tent. And part of that tent is a solar panel that powers the station and is facing north. Alongside those challenges, we have other challenges as well. Wildlife, they love to mess around with our stations. Cattle, they like to lay down on our stations, and they like to chew our GPS cables. They love that. So it's not just seismologists that are interested in this. I don't know, cattle for some reason are also very much interested. But I would like to acknowledge all the people and all the teams at GA that have helped us getting this done. Access engagement, field operation and engineering support, contracts and procurement, observations and system support that are running the Australian National Seismograph Network, mineral, energy and groundwater information support, EFDF Program Management Office, RAPI Resource Program Delivery and Support Team that are continuing this project, and the senior executive teams all have contributed. This wasn't a teamwork, this was an organizational level work that many teams worked together to get this done. We got really a lot of help from state and territory partners, academic partners, and industry partners that to get this done. Okay, so back to seismology. Let's see an application of that workflow to Australia. Australia becomes ancient as you go towards west, and it becomes younger as you go towards east. And this spans 4.4 billion years of Earth's history. Very complex geology. On top of that, we have many sedimentary layers that are stacked on top of each other with different ages. And on top of that, we have the largest groundwater reservoir in the world, maybe one of the largest groundwater reservoirs, the Great Artesian Basin. And all of these will affect seismic tomography. So in order to describe these features, I'll go through layers one by one. Sediment, crust, moho, lithospheric mantle, lithosphere-asthenosphere boundary, LAB, and then maybe convecting mantle, if time allows. Before I do that, I want to do an acknowledgement of the previous work that has been done. Throughout the years, ANU and specifically have done a lot of work in imaging the Australian crust, given the data that they had. This is the first ambient noise tomography study done by Sagan and Kennett, 2012. There's a 1 second image, there's a 3 second image. You can think of those as slices through 1 kilometer and 3 kilometer. But you can see the data coverage. It's not that good. It's just a few points in Central Australia and a few points in Western Australia. The data has improved. The data coverage has improved in 2023, which is a CSIRO, same team, Sagan and Magrini et al., but all the models are different, okay? So I'm going to keep the Sagan and Kennett in this corner as a reference, and I'm going to show you the coverage that AusArray has brought. This is the real data coverage from AusArray deployment. You can see that the ray coverage is now evenly distributed across the continent. And so AusArray and ANSN together provide an even coverage of broadband data across the continent for us. And the new dispersion curve algorithm pushes the imaging to higher and higher frequencies. So that image is now my image, is now the image that we have generated using all of these data. This was generated about 3 weeks ago, okay? We got the last bit of data about 4 weeks ago, so this will be improved, but I'm already quite happy with how this image looks like. So let's make some comparisons with what we know about the Australian geology. The Great Artesian Basin, these areas are water saturated, okay? And that's exactly when we see extreme low velocities with the same shape in the ambient noise tomography model. We also see other basins. One is the Canning Basin, and the other one is the Officer Basin. Great Artesian Basin and the Surat Basin, all showing up within the boundaries, more or less within the boundaries that are drawn from the surface geology. And also other basins, the Perth Basin, Beetaloo, Carrara, Darling, Amadeus, you name it. Anything that you would expect, I would say, have shown up here. Okay, so that's another validation of the model, but also when we look at the cratons, the Western Australia craton, the Yilgarn and Pilbara, they are showing up at high velocities, but there are still variations within those cratons, which is quite interesting. The Gola craton in South Australia and then North Australian craton is also showing up as high velocities. So very interesting, very reliable results, I believe. Now, let's look at the cross-section. Those were sections through frequency. We can convert those frequencies in a transdimensional hierarchical Bayesian, so it's a probabilistic workflow that converts those frequency images into a depth image. It's a 3D depth image. And I won't go into detail of what's going in. Those are the references if you like to read. But let's take a look at a cross-section through the crust and the sedimentary layer from A to B. It's west to the east of the country. I've particularly picked up this because it goes from where the Australian gravity is low in the west and then suddenly jumps to a high gravity and then stays high throughout the rest of the country. Also, I'll be making a comparison with AusMoho, Brian Kennett's Moho, and another comparison with AusSeabase that gives us the depth to the basement. A cross-section through A through B, from A to B, and a comparison with AusSeabase. This is a top 20 kilometer of the crust, okay, 0, 10, 20. The black line is from AusSeabase, okay, and the background image is from ambient noise tomography. You can see that in the Officer Basin, the AusSeabase team believed that the depth of the basement is quite deep. It goes down to 7, 8 kilometers. That's not what we see in ambient noise tomography. I believe they might be overestimating the depth of the Officer Basin here. But I'm pretty sure that in the Great Artesian Basin, they are underestimating the depth of the cover because you can see, I'm not sure how clear it is, but this is the black line from the AusSeabase data, but these low velocities are showing you the deepest part of the perhaps water-saturated sediments in the Great Artesian Basin. Same goes with the Surat Basin. Now let's take a look deeper and then look at the whole crust and make a comparison with the gravity data. So this is a cross-section through the gravity data. You notice that the gravity from west of Australia gradually decreases and then it suddenly jumps and stays high throughout the rest of the country. So how does that look like when we compare it to an ambient noise tomography? Well, you can also see that the MOHO, just like the gravity signal, is also deepening, and then around the area where we have this jump in the gravity data, that's when the high velocity material are coming up. So if we draw a MOHO proxy, velocities of 3.8 kilometer, that's just about above the MOHO, and 4.4 kilometer, that's just below the MOHO. You can see that in areas that those two dash lines are close to each other, that's where you have a sharp MOHO. And in areas that those two deviate from each other, that's where you don't have a clear MOHO. It's just a gradual increase of velocities. But it's quite interesting to see where this gravity response, this increase in gravity, correlates well with the increase, with the shallowing of the MOHO and also having higher velocity materials beneath there. Okay, so that was the crust. Now let's go deeper. MOHO, there's already a MOHO map for Australia called AusMoho by Brian Kennett. I want to make a comparison between Brian's MOHO and the gravity map of Australia. And I'll make that comparison in Northern Territory. That's where we have a dense deployment, the first phase of AusArray. Brian's MOHO is quite smooth, okay? The features in there, they're quite smooth, and I believe it doesn't really correlate with the extreme features that we see in the gravity map. We have the world-famous high gravity here that doesn't really, I mean, there is a bit of a signal there, but it doesn't really correlate with what we see in the gravity map. I have picked MOHO using our data and using receiver functions that I'll show you a cross-section through, and that's what my MOHO looks like, okay? It's quite patchy, it's quite, it has a lot of detail, but I'm gonna argue the case. I'm gonna argue the case of why I think the Australian MOHO at high resolution would actually look like the image in the center. Okay, and I will be looking at the cross-section AB that goes through starts from this low gravity, goes through the high gravity and continues north. And I'll show you cross-section through Brian's MOHO and my MOHO. So the first evidence comes from this study done by Bruce Colby and Brian Kennett in 1989, and this was a tiny, it was a very small active seismic line that with GA actually conducted over this gravity high, and their interpretation is actually quite interesting. They're saying that the layers within the crust, they're not placed like this, they are placed like this, okay? So they're saying that the lower crust is coming all the way up to the surface, and that's shown in this 2.87 density area. So they're saying that in this region, we have a double MOHO. One MOHO goes above the other MOHO, and the lower crust goes all the way to near the surface. So I want to see this. I want to see how does the receiver function, which images the MOHO, and passive seismic, and my ambient noise tomography, whether it matches this or not. So that's what the receiver function cross-section would look like. The image on this screen is not great. Hopefully if I put my interpretation on top, it would be clear. So you can clearly see that my interpretation of MOHO has a jump in it. It's very similar to what they have predicted as a jump in MOHO. And then the MOHO continues, goes down, and then it kind of disappears and it comes back and goes up again. And when we look at the ambient noise tomography results, and I've superimposed my interpretation of MOHO on top of that, we could see more or less the same features, okay? The MOHO deepens. Let me bring in the MOHO proxies. So 3.8 kilometer, that's above the MOHO, that's below the MOHO. And you can see that there are areas where these two really separate from each other, they widen up, basically. And that's where this low velocity material is coming up. But this high velocity material is coming up that matches nicely what they predicted as lower crust coming all the way to the surface. It's exactly this high velocity material coming up, okay? So, and I've plotted also Oz MOHO on top of this, so you can see that Brian's MOHO doesn't really capture these detail, okay? It's sort of an average MOHO throughout the whole area. It does capture some of the features, but not all of them. So I think that's what that would be our argument for the future of that work. We will continue to do that throughout Australia to image MOHO across the continent at that high resolution. Okay, final image. Hopefully I have 1 or 2 minutes still. Okay, great. So LAB. Okay, the LAB is the lithosphere-asthenosphere boundary, is the mechanical transition from the Earth's rigid outer layer, the lithosphere, to the weaker ductile asthenosphere below. Okay, so it's just this bit over here. Now, there was an LAB MOHO that Hogarth and Carroll contributed to this work, and then this came out in the first phase of Exploring for the Future program, and they've realized that the location of the large deposits correlates with the transition, LAB transition. Okay, that's where the LAB goes from thin LAB to thick LAB, and that correlation is shown here. That's the location of large deposits and the contour of the LAB at 170 kilometer. Excuse me. At 170 kilometer, that seems to correlate with each other quite well. Well, this LAB map was derived from a model by Fishwick and Rawlinson, 2012. And there's a procedure to convert shear wave velocity to temperature, which then you derive LAB from that temperature model, okay? But the question you can ask is that why that model? There are many other models that you can use, okay? And I can tell you that if you used other models, that LAB map would be different, okay? So one of the aims of continuing AusArray and what the data that we have recorded and the future data that will be coming in is to try to develop a new mantle model so that we can develop a new we can develop LAB models, but with a variation. I would like a variation in there that I will explain in a moment. So we've already done this in a pilot study. We partnered with a company called Mondijk, based in Switzerland, that I visited about 2 weeks. Visited them about 2 weeks ago. They have a software called Salvus, and we're trying to talk to them to modify Salvus to match our needs and what we want to do. So we have this AusArray distribution. We have the software, and Australia is surrounded by earthquakes. Okay, so it's a perfect natural environment to do a full waveform inversion, where the sources are surrounding the medium and the medium in the middle is covered with stations. And so this is what our model looks like. It's a preliminary model. We just run the software using the data that we have, using the only first half or maybe 6 months of the data that we had. Okay, so if we convert this VS model, that's what the LAB looks like. If I make a comparison with the previous model of LAB, a lot of the features are exactly the same. Okay, there's Gola Craton there, there's Gola Craton there, these deep LAB up there, deep LAB down there. So lots of similarities, but with tiny difference. This 170 kilometer dash line that was drawn in this study is now further out. Okay, so the purpose of this work was not to say which model is better or which LAB is correct. The purpose was to say, if you change your VS model, your T model is going to change. So the future work here is not to generate, we will do more iterations of that full waveform inversion, because that's a new model, it's interesting in itself. But I would like to develop a different workflow in which that would be an ambient noise tomography model, in which we go from error in the data. We propagate the errors in the data through a probabilistic workflow and generate an ensemble of VS models. From that ensemble of VS models, we generate an ensemble of T models, okay, temperature models. And then we will have a mean of temperature and a standard deviation, an error bar, basically. That's the way I believe that we can reconcile the ambiguity in the data, the differences in different velocity models, into a temperature model. Okay, so I think that comes to an end. So EFT of achievements, AusArray Northern Territory deployment of 50 kilometer, AusArray 200 kilometer across the country. First images of the sedimentary cover looks promising. Complex MOHO, very interesting. We would like to continue that. Deep mantle and LAB, we will be looking into that. And the rapid outlook for all of these is that AusArray will continue and will cover the whole country at a 50 kilometer spacing. More detailed images of sedimentary cover will come out. Complex MOHO across the continent, deep mantle, and hopefully a probabilistic image of the LAB. Thank you very much.